from Colorado School of Mines. I've known Piret for many years and always admired her work. She's definitely one of the experts on tidal deposits in the rock record. So let's hear from her talking about towards morphodynamic and sedimentary models of tide influence and tide-dominated deltas. Thank you, Piret.
Well, little did the session organizers know that this talk is not about the ancient sedimentary record, although many of the questions come from there, from working in the ancient record. But I think everybody here knows that it's not so easy to interpret the ancient record. And it's not easy to interpret the modern record either, because we only see so short periods of time. So here is one of the attempts to try to combine. So many questions come from work in the ancient, but what I will actually present today is mainly some modeling results, as well as comparison to the morphology of modern deltas. And we also key this into a literature review of ancient tide-influenced and dominated deltas. So the general question is, what effect do tides have on deltas? And why do we care about this? Well, firstly, river deltas are economically and ecologically the most important environments in the world. So we clearly care about the deltas, and especially because these deltas are highly vulnerable to global change. And even more though about strongly tide-influenced or dominated deltas, if you look at this diagram down here, more than half of the water discharge and almost half of the sediment flux comes to global oceans through tide-dominated deltas. So they are especially interesting. And the predictions are that through global change, the tidal influence to deltas will increase because of the decreasing river discharge, because of damming and irrigation, as well as because of the sea level rise. And that's kind of what this diagram tries to show, how the arrows shift from river dominance towards tidal dominance, but also wave dominance, but we are not going to touch this side here. So, in addition, so because of these two processes, we expect that the deltas are globally losing area, that there is a land loss going on. But, interestingly, it has been suggested that tide-dominated deltas are gaining land rather than losing land in current conditions. So, the land building processes may differ in strongly tide-influenced deltas versus other types of deltas. From the sedimentary record, there is a variety of publications on tide-influenced and tide-dominated deltas, but if we look more closely, almost none of these publications actually presents any criteria or even attempts to present criteria. Why do they call a delta tide-influenced delta or tide-dominant delta? Which raises the question, does it even matter? So coming back to what Allard says, is this one of these important things we need to differentiate in the sedimentary record, or maybe not? So my goal here today is mainly to present you some aspects of the DELS 3D modeling results, and with the aim to explore the relative roles of tides and river discharge, and to quantify some of these controls. In addition to this, through this work, we also proposed some non-dimensional morphological criteria for recognition of tide-dominated and tide-influenced deltas, but I will touch this very, very briefly here. And these criteria are really easy to use because they can be just used on satellite images, and we tested them on 30 modern deltas. So we will discuss rather the delta building processes, the global change, and then whether this work has any implications for understanding the ancient record. So the modeling. We based our DEL 3D model on the Fly River Delta. So we use the tidal range, we use the river discharge, we also use the type of sediment, the geometries, everything from the Fly River Delta. And then on top of that, we played around with the tidal amplitude and river discharge. And that generated kind of this matrix of simulations, of 30 different simulations. And what is different in our modeling efforts from previous attempts to model tide influence deltas is that we allowed for erosion of the shorelines. So because of that, we could generate these adjacent tidal channels as well as allow the distributary channels to kind of erode landward. And we did this because one of the characteristics proposed for tide influence and dominated deltas is the seaward widening of the channels. But just looking at modern deltas, it also looks like the channels are extending landward. And then we analyzed all the differences that we could find, and we quantified these differences. And just to get started with, we used the previously proposed criterion for differentiating tide influence and tide dominated deltas, which is the t-value that compares the tidal discharge amplitude to river discharge. And so if that is larger than 1, then a delta is tide dominated. If it's lower than 1, it's river dominated. But the problem is that in order to use this criterion, you need the data on the tidal amplitude as well as river discharge, whereas we were interested in providing morphological criteria that you can just use on images and even use on aging record. So here are the results. So we have river discharge change and tidal amplitude change, and as you see, we've produced a wide range of different morphologies. And according to the t-value, then the tide-dominated deltas are in the upper corner, kind of separated by this dashed red line, and the river-dominated or tide-influenced deltas are on the lower corner. So all the deltas I'm talking about in these presentations are tide-influenced. Even if I say river dominate, they are still tide influenced. Okay, so I'm just going to show a few of the aspects that were interesting. So since seaward channel widening is one of the criteria that has been proposed for these kind of deltas, then yes, we see seaward channel widening in all tide influenced deltas. But perhaps more interestingly, we can quantify that in tide dominated deltas, the seaward widening occurs across the whole delta domain, whereas in tide-influenced deltas, only that the seaward channel widening only occurs in the seaward part of the deltas, and we were able to quantify that in most tide-influenced delta, that's limited to only the seaward 1/3 of the deltas. So what this means, for example, for the sedimentary record, is that in tide-dominated deltas, we should expect to see tidal signatures throughout the delta, whereas in tide-influenced deltas, only in the outer parts, on the seaward parts of the deltas. Oh, by the way, like the diagrams that you're looking at here, on the horizontal scale, there is river discharge, on the vertical scale, there is tidal amplitude, and then these lines kind of trace different metrics. So essentially, if you see the lines changing in a vertical sense, that means that the tides are in bottom control. If you see them change, if you see them on the horizontal scale, that means river discharge is an important control. And the pink corner indicates the tide-dominated deltas according to the t-value. So one interesting result is that the delta length is controlled by different processes in tide-dominated versus tide-influenced deltas. So in tide-dominated deltas, if you look at the pink corner, the delta length increases with tidal amplitude. and it's independent of river discharge. Whereas in tide influence deltas, the delta length increases with river discharge and is instead independent of tidal amplitude. So that's quite interesting because it tells us that the land building processes must be different and that these processes are threshold driven. So in tide-dominated deltas, the delta length of propagation is a function of distributary channel elongation and mouthbar elongation, whereas in river-dominated deltas, that's instead mouthbar aggradation, bifurcations, and avulsions. And of course, because of that, we can say that river and tide-dominated deltas will react to global change in a different way. It looks like the text is messed up, but that's how it is. So, so they will react in a different way. And another interesting aspect is that, yes, the tide-dominated deltas can build delta length, but if you look at these two examples here, yes, it's the same length, but if you look at the land area, then it's quite different, because the distributary channel area has a large component in tide-dominated deltas. And we can also quantify those aspects, and also the delta width tends to be much wider in river-dominated deltas. We also looked at the tidal channel morphology, but I'm not going to go into details here. So what did we learn? So land building processes differ. So clearly we want to differentiate these deltas in modern environments. And the key difference is these land building processes. And because of that, the river versus tide-dominated deltas will react differently to global change, meaning that tide-dominated deltas are less sensitive to river discharge changes, meaning things like damming or irrigation, whereas they are more sensitive to tidal range changes such as a result of sea level rise. Whereas river-dominated deltas are less sensitive to sea level rise and more sensitive to river discharge changes. And I didn't really talk about the tidal channels, but we really see that the strength of the tidal reworking in kind of adjacent to the axial delta in the tidal channels themselves, as well as within the distributary channel area, is quite similar. So the tidal channels tend to extend seaward quite far, and that changes the shape of the coastline. So this is one of the metrics that can be used, essentially the angle of the protrusion of the delta that differs in tide-dominated and tide-influenced deltas. And there are also some other morphological criteria that can be used. So what about the sedimentary record? We do think they are distinct, and one of the key distinctions really is what I already mentioned, that in tide-dominated deltas, we should expect to see tidal signatures throughout the succession, whereas in tide-influenced deltas, only in the kind of seaward portions of the deltas. And we do think that we see this in sedimentary record, at least in a few examples that we have focused on so far, where there are examples of deltas that lack the mouthbar and distributary channel complexes kind of in the delta plane successions, and they only have deep tidal channels and some tidal flap fascias, and then the tidal bars in the delta front. Whereas in other deltas, we see just as many tidal signatures in the delta front, whereas the delta plane is clearly distributary channel and mouthbar complexes. And in addition, in the first type, in the tide-dominated deltas, we see that the distributary positions are very stable, whereas in the tide-influenced deltas, we get delta lobe avulsions, and the stability there is much lower stability there. So I leave you with that. Questions?
Thank you, Pirata, very Other questions for Pirette? Sergio?
Okay, thank you for this presentation. And the criteria that you presented are based on the geomorphological and aerial distribution of tide influenced versus tide dominated processes. And my question is, what do you expect to find when you consider in a cross-sectional view this important depositional system, which is the more, let's say, recurrent window we use in the rock record? What do you expect in terms of difference between these two types of system?
So the difference is we've noticed in some of the systems, like our group has worked with, is kind of what I said, that in tide-dominated deltas, you see the tidal signatures throughout. So you don't have the mass bar and distributary complexes on delta plane. Rather, you just see deep tidal channels and like some tidal flat fascias. And yeah, so no river-dominated topset. Whereas in tide influence deltas, the distributary channel and mass bar complexes are present, and they don't have as many tidal signatures as the delta front, but the delta fronts can look very similar.
So basically the difference is on the delta, the top set.
The top set, exactly.
Okay, thank you.
Justin?
How do you handle the different size of sediment transport coming to the area?
Can you specify? What do you mean by different sizes? Oh, you mean like the sediments versus
some areas will have a large sediment input and some
Yeah.
areas will not.
So if you refer to the modeling, then that is very simplified, right? So it's just that the discharge is linked to water power, is linked to how much sediment it's able to transport. So this modeling does not take into account in differences in sediment supply. So that would be another layer that needs to be added.
So you use a sediment transport model for alluvial channels or something like that?
It's simpler than that, it's just physics. How much water power do you have, how much sediment, given the sediment grain size in the model, it's able to move.
Thank you.
Are there other questions? Yes? Michelle?
Thank you. Yes, I wondered, you modeled this progradation of the delta with different parameters, and it shows this nice morphological change. And I think you mostly showed the width change, but this morning Anna showed in the slide there are nice other morphological changes. Especially I was interested in the bathymetry, if you have modeled anything like that, or the sinuosity as well.
Yes, so like in our model, we haven't looked at the sinuosity because that's kind of detailed in our model, but we haven't analyzed the bathymetrical data yet.
Okay, because the bathymetric data are very interesting. Actually, in the fly as well as the other tidal deltas, the channels get very shallow toward the mouth, which it's a bit different from what you say that in the ancient you get these very, very deep tidal channels with tidal flats when you have tidal systems. I see the opposite in the Mekong and other systems in the model.
Well, like in the ancient, you can't really map out if they are deep along the whole delta, right? You know that they are deep in certain parts of the system. Like it's very seldom you can map the whole thing out.
Thank you.
Okay, thank you very much.